consent. And let's present. Share. Yes. 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 Okay. And things are working. Okay. Last year, you learned how to do electron configurations, like over here, and you didn't learn any exceptions. In first year, we just keep things basic, and then this year we can build and we can improve where mistakes were made, and this is one of them. It turns out that sometimes electrons jump from one orbital to another one, and the reason is because it provides lower energy. Lower energy is like your wild card way of explaining things. If you're ever asked to explain something and you don't know what to say, a good guess is lower energy, and in this case, it is the correct answer. So notice these. This one here, the 4s, only has one electron. This only has one electron. 5s only has one electron. And the 6s only has one electron. What's happened is an electron has jumped from an s, and it's jumped in all of these cases to a d where there was a spot. The reason is because it makes overall lower energy. A really good example is this chromium right here. Chromium normally has a 4s2, and it normally has an empty orbital right here. So what happens is this electron says, hey, I can go over here, and then I won't have to share space anymore. And you end up with a 4s1 and a 4d5. And everybody is unpaired. And that's a good thing, because that's Hund rule. Hund's rule says the electron, whenever possible, prefers to be unpaired. Now, sometimes it's not worth it, because you might be thinking, well, why don't all the electrons stay unpaired? So for example, in chromium, why don't the 1s electrons stay unpaired? It's because it's a trade-off. The only way for these to be unpaired is for this to jump to some much higher energy orbital, and that's not worth it. So that's why not everybody does this. They only do this when it works out really nicely for the entire atom. Here's another example with copper. Same thing. One of the s electrons jumps. In this case, you still end up with a pair over here. So it's not as satisfying as the chromium. The chromium is a very nice example. You can clearly see why. This one's not quite as satisfying, but it does happen, and it does still lead to lower energy. And the only 4 you need to be aware of are these 4. There's a bunch more. Like if you look on a periodic table that has the electron configurations for each element, you'll see all sorts of exceptions, especially once atoms get big. All right, excited state. First, let's talk about not excited state. So a normal electron configuration is called normal or ground state because all the electrons are in their lowest energy, or resting. Sometimes you might see resting state, and that's what we have here for oxygen, and that's normal. What can happen is one or more of the electrons can get hit with energy, and it jumps to a higher energy orbital. And that's what happened here. One of the 2p electrons has jumped to the 4s. Now, why did it go from 2p to 4s? Well, that must have been the amount of energy. It must have been just the right amount of energy to make this jump. Now, this one only has one electron that's been excited, but you can have more than one. So it can be one or more electrons. I've seen students confused on that. So let's do another excited state for oxygen. For example, I could also do 1s2, 2p1, 4s2, 4d, let's see, 1, 2, 3, 4, 5, 3. In this case, These ones are still in their resting state, but these ones are all excited. So we would say that there are 5 excited electrons and 3 resting electrons. Impossible means impossible. It means that something has gone wrong. This can't happen. In this case, it's the 4s3. S can only have 2 electrons, so that's not possible. Another common impossible one, and this one is really good at tricking you, would be a 2d10. There's nothing wrong with D10. That's fine. It's the 2D. You can't have a 2D subshell. They start in the third. Moving on. This chart shows as you fill in the orbitals, you start with the low energy, which of course is why we do a 1s first, then higher is 2s, then 2p, and 3s. This is just a diagram that shows the energy. You know this already. When you do your electron configurations using the periodic table, you do this already. But you might see this chart somewhere, and now you know what it is, and it's what you already know. Okay, shapes. S, most people refer to it as a sphere. P, I like to say peanut because it matches. D, I like to say double peanut. It's not exactly right, but I just like the fact that it starts with a D. And F, I like to say flower. And so let's take a look at some of these things. I have a picture of them here. And in this picture, they show an S, they show the 3 Ps, the 5 Ds, and the 7 Fs. Now, what you need to realize is these shapes don't exist. They're not real. If you were to look at an atom, if you had special magic eyes, and you could look at an atom, you would not see these shapes. You would not see this sphere and these peanuts and these double peanuts and such. It's too bad because it would look really cool if they really did exist. What they are is regions of space where the electrons reside. So you could have 2 electrons in this d orbital. You could have another 2 in this d. You could have 2 in this p. You could have 2 in the s, and so on. So it's just a region of space. It's a zone. Now, you did a lab last year that was related to this, in which you dropped a bunch of darts on a target. Most students leave that lab thinking that was fun, standing on the tables and dropping darts, and that's all they get out of the lab. But the point of the lab was it was an analogy to this. After you dropped the dart a bunch, you started to see a pattern on your target. That pattern was showing where the dart is likely to land if you were to drop it again. So it was a probability of where the dart would land. These pictures are probabilities of where the electron is. And that's that. Some of them are really weird too, like the flower here. That's already weird, but look at that one in the middle. It's like a peanut with 2 donuts. Very odd. Back to our stuff, which is here. Okay, shorthand. I'm not a big fan of shorthand. Shorthand kind of is like a step that gets you to outer. It's outer that we care about because these are the electrons that are bonding. So for example, if you have a molecule like this, these electrons here that are being shared amongst the 2 chlorine atoms, those are from the outer shell. And that's why they're so important. If you have an ionic bond, like sodium, giving an electron to a chlorine atom, that happens in the outer shell. So that's why this is so important. And this is just the same as last year. The outer shell for bromine would be 4s24p5. Another way of saying that is 7 valence electrons. Remember, the outer shell will never have Ds or Fs. The outer shell will either be S by itself or S and P. That's it. Okay. Ions. Remember, electrons are negative. So when you gain electrons, you become more negative. When you lose electrons, you become more positive because now the protons are outnumbering the electrons. So take a look at this example with N minus 3. Nitrogen normally is 1s2, 2s2, 2p3. But if it gains 3 electrons, they go into this p, and that's why you end with a 2p6. Now that's the same as neon, or O minus 2, or F minus, or Na plus, or Mg plus 2, or aluminum plus 3. They all have the same electron configuration as neon, but realize they don't become neon. When this happens to nitrogen, nitrogen just goes from normal to minus 3 ion. It's still a nitrogen atom. It doesn't become neon. The only way to change it to neon is to change the number of protons in the nucleus, and we're not doing nuclear things right now. Be careful with the transition metals. So look at iron here. This is iron's normal electron configuration that you would do. If we wanted to make a +3 ion, you have to be careful where you take them from. Don't take them from the 3D at first. You want to start in the outer shell. And in the case of iron, the outer shell is the 4s shell. So the first thing you take off is the 4s2. You get rid of that. And then you have to get rid of one more. And that's why you then take one from the 3d6. And so then you end in a 3d5. This is just the ending right here. I've ignored the earlier electrons. This shows why iron is so happy with a +3 charge. Is because if you take iron's normal situation of its 3D, like this, you've gotten rid of the 4s, that's gone, and now you get rid of this electron, and you end up with this very satisfying situation here, and that's a low energy situation. Now right here, I have a chart of low energy happiness. This is the low energy happy chart. This is what everybody's trying to do. The universe is lazy. Everything in the universe wants low energy. So atoms, when possible, they want to have a full shell, like an octet, because that's low energy. Next best, if you can't get a full shell, would be a full subshell. Next best, if you can't get a full subshell, a half-filled subshell. And that's what we have right here, is a half-full subshell. And it's not the best possibility, but it's the best that iron can do under these circumstances. Next, this is a technique. It's called photoelectron spectroscopy, or for short, most people just say PES. And it just means photo, light, electron, electron, spectra means different energies of light, and scopy is just to look at a spectrum. So what it basically is you take an atom like chlorine, you zap it with light of different energies, and you see at what energies do the electrons fly off. So you monitor the chlorine, and every now and then some electrons will take off. They'll fly away from it. And that's what this x-axis is here. So notice it's high energy on the left and low energy on the right. So that's backwards from normal. Normally when we do a graph, we would do energy that way. So it's, you have to be, and they're always this way. So just be used to it. So what you'll notice is if we took a chlorine and we started zapping it with energy, we would find at this energy here, 5 electrons would fly off. Then at this energy, 2. Then we keep increasing the energy, and 6. Increase the energy a little more, 2 here, and finally 2 here. And what's happening is the height of each peak is relative to the number of electrons. So that's why all the s orbitals had this same size peak. Notice the p's are different because this p here had 6, so that's why it's on the 6th little line. But this p only had 5. It didn't have a 6 electron, so that's why it's only that high. So there's two things to realize. The height is relative to the number of electrons, and where they're at on the x-axis, here, here, and here, is based on how much energy it takes to get rid of them, and that means you're getting closer to the nucleus. And I made a note here. This 1s2 takes the most energy because you're getting so darn close to the nucleus, it's holding on to it really tight. So for example, let me get rid of some of this stuff here. If I had a nucleus and I have an electron here, let's say in the first shell, and I have an electron here in the second shell, there is going to be an attraction between the nucleus and the electron. The electron in the first shell, that's going to be a stronger attraction between these two things, between the nucleus and the electron. So that one's going to be harder to get out there. And that's where Coulomb's law comes into place that I mentioned the other day. Coulomb's law says the closer these things are, the stronger the attraction. So when we start zapping this with electricity, this one is going to fly off easier than the one in the first shell. And you see that here with all the different orbitals of the 3p5 and the 3s2 and so on all the way down to the 1s2. So let's take a look at an example here. Now I like this example, and it brings up two important things. First, it's a PES example, so good. The other thing is these statements. All of these statements are very sciencey. They all sound good. And some of the statements are true. So what's tricky is you don't just look for the only true statement. You need to find a true statement that explains this scenario. Because, for example, the correct answer is A, but B is true. The statement in B is correct. It just doesn't explain what we're seeing in this phenomenon. So let's take a look. We've got lithium and beryllium. It makes sense that beryllium's peak is twice as high because beryllium ends in a 2s2, but lithium is in a 2s1. So that makes sense. The next thing is, notice beryllium's 2s peak is right about at an 11 in terms of energy, whereas the 2s in lithium is right around a 5. I'll just write that. So it's about a 5, and this is about an 11, showing that it takes more energy to knock electrons off of the 2s orbital in beryllium. And that's why A makes sense. Beryllium has a greater nuclear charge. What that means is more protons. Beryllium, of course, has 4 protons. Lithium only has 3. And so the fancy way to say this, instead of saying beryllium has more protons, the fancy way is to say greater nuclear charge. You'll get used to these phrases over the next few weeks. Also, beryllium has more electrons in the 2s orbital. And so we see that. It's twice as high. Let me switch colors here. Twice as high, and it's higher energy. Now let's take a look at B. I'll get this out of here. If we look at answer B actually is a good statement, but it doesn't match this chart. Beryllium electrons experience greater electron-electron repulsion. That's true because in beryllium, it has 2 electrons in its 2s subshell. It has an electron, it has another electron. Whereas lithium, this is beryllium, is only 2s1. That means these 2 electrons are going to repel each other. They're also going to repel the electrons in the 1s as well. So this statement that beryllium has greater electron-electron repulsion is correct, but that doesn't explain the chart. That would only be the right answer if beryllium's energy here was lower, like if it was over here. That would be explained by answer B. So you have to be very careful on these types of things and don't just pick the first thing that makes sense by itself. It has to match the chart. And the AP exam loves this stuff. They love to give you a scenario and a bunch of statements, and you have to decipher which one is the correct one for that scenario. We'll do a lot of this in class. Moving along, quantum numbers. Last year, the best that we did was orbital notation. So for example, you might say 2p3, and you would do this. And what you could say is that this electron right here, for example, you could say it's in the second shell. You could say it's in a p subshell. You could say it's in that orbital, meaning the line right here. And you could say that it either has an up spin, or you might have learned last year that it's called positive 1/2. Well, it turns out there's a way to do this with numbers only. And it's called quantum numbers here. You'll notice I mentioned it's not on the AP exam, but I still want you to know it because it gives you good background. And so I'm going to show you how to assign quantum numbers. It's pretty easy. The first quantum number, the level or shell, is the same. You already know it. It's, in this case, 2. So that'd be 2. The second quantum number is the sublevel or subshell, and that's here. And S is a 0, a P is a 1, D2, F3. So just remember to start at 0 and you'll be okay. So in this case, because it's a P, we would say 1. The third is the orbital. And so to do this, you must do orbital notation like I've done here. And there's also an example with a D and an F. And notice you have to set up a number line. Always put 0 in the middle, and then do positive to the right, negative to the left, like a classic number line when you're learning how to count in math. So in this case, this would be the 0, and this would be a +1 orbital, so my next would be +1. You don't have to put the plus, but I like to emphasize it. And then the last is the spin. And up is a +1/2, a down is a -1/2. So since this is up, we would go +1/2. And those would be the 4 quantum numbers for just that electron that I circled here. So take a look at this example, this one with bromine. Bromine ends in a 4p5. It says it wants just the last electron. You could do this for any electron, but normally we look at the last one. And so you have to do your orbital notation. So 4p, you could label it if you want. And it's got 5 electrons. Make sure you do this in the correct order. 1, 2, 3, 4, 5. Because if you do it in the wrong order, you'll be talking about the wrong electron. We're talking about that electron right there. And so when we assign our quantum numbers, well, 4, okay. That was easy. P, if S is 0, P is 1. It's the center orbital, and the center orbital is always a 0. And it's pointing down, so it's a -1/2. And I have another one here with the last star electron in uranium, same idea. This is just a really corny joke. And that pretty much does it for this lesson. I'll stop my recording right now and then talk about the homework